So all everyday matter is made of atoms. Atoms are in turn made of electrons, protons, and neutrons. My research goes one step beyond that, studying what's inside the protons and neutrons. So what the inside of a proton looks like depends on the resolution with which you look at it. In general, when we want to image or detect objects, we often use waves to do that. We can use visible light waves like we do with our vision. We can use other forms of electromagnetic waves such as radar, or we can use also millimeter wave scanners, like most of us who came through airport security on the way to get here probably went through. We can also use sound waves to detect objects like bats do when they use echolocation to detect insects to eat. Or you can use particle waves, thanks to something known as wave-particle duality in quantum mechanics. So the proton is made of subnuclear particles known as quarks. These quarks are held together by gluons. Yes, gluons are named after glue because they stick the quarks together. We physicists like to think we have a sense of humor. If we go to wavelengths that are short enough, we can actually detect those quarks and gluons inside the proton. So how small wavelengths do we need? Well, the proton radius is about 10 to the minus 15 meters, so a femtometer. This is 1,000,000 times smaller than the smallest nanoscale science. So we need to go to high-energy particle waves that have equivalently very short wavelengths in order to do this. So one of the facilities that I work at is the Large Hadron Collider at the European Center for Nuclear Research, known as CERN, that's a French acronym. It is near Geneva, Switzerland. So here's the Geneva airport. This is La Commande. The facility goes across the French-Swiss international border. It's about a 17-mile ring. There are two counter-circulating beams of protons. They collide at two giant experiments, one of which I work at. So the one I work at is called LHCb, for the Large Hadron Collider Beauty experiment. Beauty is a type of quark. It is about 4 stories tall. The detector weighs more than 4,000 tons. It's about 100 meters underground in the French countryside. It's right by the Swiss border. It's a collaboration of about 850 scientists, supported by 450 engineers and technicians. We're from 18 different countries. Here you can see this is a visualization of the particles produced in a proton-proton collision, which would happen right around here. In the photograph, it would be off to the left here. This is all part of our detector. You can't even see a lot of it. Thanks to Einstein's famous equation, E equals mc squared, the high energy in the proton-proton collisions that were given by the accelerated beams, that high energy can be transformed into matter, so massive particles. Those particles spray out in every direction. The ones that happen to go in the direction of our detector are the ones that we can see. So this is an actual image, visualization. Color, is artificial, obviously. Computer-generated colors here of an actual proton-proton collision, and these are the particles streaming out of the detector, and the different parts, sort of the different things you can see here, are the different components in our detector that detected where they passed through, where they left energy, where they knocked off some electrons, ionized atoms, and then we can see where those particles passed through. So we do this trillions of times to collect a lot of statistics. I also work at another facility that's much closer to here, basically straight south. The Relativistic Heavy Ion Collider at Brookhaven National Laboratory on Long Island is the only collider facility in the US currently. Here you can actually see on Google Maps, this is the ring. It's not actually the accelerator structure, it's the access road to access the different areas around the accelerator. Here's a photo of me inside my detector there. Doing some work inside of it. I've been working on this experiment since 2001, so these are very long timescale experiments. So they require a lot of resources to build and operate, but they also run for many, many years typically. The Relativistic Heavy Ion Collider is Brookhaven National Laboratory on Long Island is also one of 2 candidate host sites for the next collider facility expected to be built in the United States. This is the Electron Ion Collider. The Electron Ion Collider is a proposed $1 billion scale facility. That would be like a giant electron microscope of several miles around. That would be capable of looking at the quarks inside protons and neutrons at resolutions previously not possible. In 2018, I was part of the National Academy of Sciences committee that evaluated the science case for such a facility in the United States. And actually, I was really pleased with the timing. So the current issue of Scientific American, this is the online version, but there's a feature article on the electron ion colliders. That's the one up here, Subatomic Mystery, Probing the Deepest Recesses of the Atom. If you want to get a new billion-dollar scale science facility built, you can't spend all your time smashing protons. You've got to go out and convince Congress that this is worth doing. So here's a photo of me in December on Capitol Hill talking to Michigan Senator Derek Peters about the Electron Ion Collider and how I lead a group of more than 850 scientists from 30 different countries that are all interested in seeing this facility built in the United States. So just a few other things you can talk to me about while I'm here. I'm also working on a new theory to refound the known branches of physics from a common, more fundamental starting point that I'm actually really excited about. If you are interested in learning more about science and you will be in this area in the summer, Brookhaven National Lab on Long Island has open house summer Sundays that are open to the public. A lot of them are very family friendly. I will also be on sabbatical in Milan, Italy, starting in July if you're going to be in the area. So thank you.